There are roughly 2 trillion galaxies in the observable universe, and the nearest one of any real size is so far away that the light leaving it right now won't reach your eyes for another 2.5 million years. That distance, that waiting, that gap between what exists and what we can ever hope to touch, that is the subject of this video. Time, not distance, not technology, not political will or funding or imagination, is almost certainly the single biggest barrier standing between humanity and the universe beyond our own solar neighborhood. And once you understand why physicists believe this, the cosmos starts to feel less like an invitation and more like a lock with no obvious key. Across the next hour or so, we're going to move through the full picture. What time actually is at the level of physics rather than intuition. What the speed of light means in practical terms for any civilization hoping to spread through the stars. How the universe is actively working against us by expanding faster than we can chase it. And whether any of the proposed escape routes from this problem, warp drives, wormholes, generation ships, microscopic laser sails, actually hold up under scrutiny. Along the way, you'll meet the scientists who built the frameworks we use to think about these questions, and you'll sit with a few hard truths that don't tend to make it into the more optimistic conversations about humanity's cosmic future. If you find this kind of thing as endlessly absorbing as we do, hitting like on this video helps others find it, and subscribing means you'll catch everything we put out. Now, let's get into it. Most people carry a working definition of time that goes something like this. Time is the thing that stops everything from happening at once. Which is funny and also not entirely wrong, but it doesn't get you very far when you're trying to understand why time is a physical barrier rather than just a scheduling inconvenience. To get there, you need to go back to 1905 to a 26-year-old patent clerk in Bern, Switzerland, who was thinking about what it would look like if you rode alongside a beam of light. Albert Einstein published his special theory of relativity in 1905, and what it said about time shook the foundations of physics in a way that nothing quite has since. Before Einstein, the assumption inherited from Newton was that time was absolute, that a clock ticking in one place would tick in perfect agreement with a clock ticking anywhere else in the universe, provided both were built identically. Newtonian physics treated time like a river, one current, one direction, the same for everyone standing beside it. Einstein showed that this was wrong. Time, it turned out, was more like a rubber band. It could stretch and compress depending on how fast you were moving and how strong the gravitational field around you was. The key insight came from the speed of light. Experiments in the late 19th century, most notably the Michelson-Morley experiment of 1887, had produced an uncomfortable result. The speed of light appeared to be the same, regardless of the motion of the observer. This flew in the face of common sense. If you throw a ball on a moving train, the ball moves faster relative to someone standing still on the platform. Light, apparently, didn't work that way. Light always arrived at 299,792,458 meters per second, approximately 670 million miles per hour, no matter who was measuring it or how fast they were moving. Einstein took this strange result and turned it into a postulate. The speed of light is constant. And if the speed of light is constant but time can vary, then time has to be the thing that adjusts to make the mathematics work. This is where time dilation enters the picture. When you move fast, really fast, a significant fraction of the speed of light time slows down for you relative to someone who is stationary. Not metaphorically, not as a perceptual trick. Actually, physically, time runs slower. A clock on a fast-moving spacecraft would tick more slowly than a clock sitting on Earth. An astronaut traveling at high speed would age more slowly than their twin left behind on the ground. This is not science fiction. It has been measured directly, most famously, when extremely precise atomic clocks were flown on aircraft in the 1971 Hafele-Keating experiment and found to have drifted by exactly the amounts relativity predicted. The numbers, once you start applying them to real travel scenarios, are extraordinary. At 99% of the speed of light, time passes approximately 7 times more slowly for the traveler than for someone stationary. At 99.9% of the speed of light, that factor climbs to about 22. At 99.9999% of the speed of light, a traveler would experience time passing more than 700 times more slowly than observers watching from the outside. In theory, purely in theory, because the energy requirements are incomprehensible, a traveler moving at close enough to the speed of light could cross the observable universe in a single human lifetime. The outside universe would have aged billions of years during that journey. The traveler would arrive, but there would be nothing to return to. 10 years after special relativity, in 1915, Einstein completed the general theory of relativity, and it added another dimension to the time problem. Not just velocity, but gravity warps time. The closer you are to a massive object, a planet, a star, a black hole, the more slowly time passes relative to an observer farther away. This isn't tiny or theoretical at everyday scales. GPS satellites orbiting Earth at roughly 20,200 kilometers altitude run their clocks at a slightly different rate than clocks on Earth's surface, due to both gravitational time dilation and their orbital velocity. The combined effect causes GPS satellite clocks to drift by approximately 38 microseconds per day relative to ground clocks. 38 microseconds sounds like nothing, but GPS systems must correct for this every single day, because uncorrected, the navigation errors would accumulate at roughly 10 kilometers per day, rendering the entire system useless within hours. General relativity is not abstract theory, it is infrastructure. Near a black hole, the effect becomes extreme. An observer watching someone fall toward the event horizon of a black hole, the boundary beyond which nothing, not even light, who can escape, would watch that person appear to slow and eventually freeze at the horizon, redshifted into invisibility, while from the falling person's own perspective, nothing unusual might be happening at all. 2 clocks, 2 experiences of the same moment, diverging completely based on gravitational geometry. One more layer. In 1908, Einstein's former mathematics professor, Hermann Minkowski, rewrote the framework of special relativity in a way that revealed something even more unsettling. Space and time are not separate things. They are aspects of a single 4-dimensional fabric called space-time. Distance and duration are not independent measurements. They are components of a single interval that observers in different states of motion will divide up differently. What one observer measures as a gap in space, another might measure partly as a gap in time. The universe isn't organized into 3 dimensions, plus a separate timeline. It's organized into 4 dimensions, woven together, and slicing through that fabric at different angles gives you different ratios of space and time. This has a philosophically disturbing implication that Einstein himself acknowledged late in his life. In 1955, weeks before he died, writing to console the family of his friend, Michel Besso, Einstein wrote, "The distinction between past, present, and future is only a stubbornly persistent illusion." That line has been quoted endlessly because it carries a weight that most physics statements don't. He wasn't being poetic. The mathematics of space-time suggests that the past, present, and future all exist with equal reality, that the universe is not a sequence of events unfolding in time, but a static 4-dimensional object in which all moments exist simultaneously. And what we experience as the flow of time is more like our 3-dimensional consciousness moving through that object along a particular axis. This view is called the block universe, or eternalism, and it remains a live debate in physics and philosophy. Lee Smolin, in his 2013 book, Time Reborn, pushed back hard against it, arguing that time is the most real thing in physics and that the block universe interpretation leads to serious problems. The debate is unresolved. What everyone does agree on is this: time is not what intuition says it is. It bends, it dilates, it flows at different rates depending on where you are and how fast you're moving. And any civilization seriously thinking about crossing interstellar distances has to grapple with this, because the physical reality of time, not just the passage of it, but its fundamental behavior, is woven into the very fabric of why the universe is so hard to cross. Before we leave this section, there's one more concept worth sitting with: the Planck time. Approximately 5.39 times 10 to the power of negative 44 seconds, the Planck time is the smallest meaningful unit of time, according to our current understanding of physics. Below this scale, the concepts of space and time as we know them lose their meaning entirely. The known laws of physics, including both general relativity and quantum mechanics, break down. What happens below the Planck scale is genuinely unknown. Some physicists suspect that at this level, time itself might not be a continuous flow, but something more like a series of discrete steps that time, at its finest grain, might be quantized. If that's true, time isn't even a smooth ribbon stretching from past to future. It might be more like a string of individual beads, each one the smallest increment the universe can produce. The implications for what time fundamentally is, at the deepest level, remain wide open. Now that the physics of time is on the table, the next piece of the barrier becomes clearer. The speed of light is 299,792,458 meters per second, about 670 million miles per hour. Nothing with mass can reach it. But before we even get to that absolute limit, the gap between current human technology and the scale of the problem is staggering enough to stop you cold. The Parker Solar Probe, launched by NASA in August 2018, is the fastest human-made object ever built. During its closest passes to the Sun, it reached approximately 430,000 miles per hour. That number genuinely impresses until you put it next to the problem. Proxima Centauri, the nearest star system to our Sun, sits approximately 4.24 light-years away. 1 light-year is about 5.88 trillion miles. At 430,000 miles per hour, the fastest we have ever moved anything, a journey to Proxima Centauri would take approximately 6,633 years. Voyager 1, launched on the 5th of September 1977, has been traveling continuously for nearly 5 decades. NASA confirmed in 2012, with a formal announcement in August 2013, that it crossed into interstellar space, the region beyond the heliopause, where the Sun's solar wind gives way to the interstellar medium. Voyager 1 is the most distant human-made object that has ever existed. It is traveling at approximately 38,000 miles per hour. At that speed, it would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. For context, the entire recorded history of human civilization spans roughly 5,000 years. The gap between what we have built and what crossing even the nearest stellar neighbor would require isn't just large, it's civilizationally humbling. These numbers represent the technology of the early 21st century. Optimists rightly point out that technology improves, and they aren't wrong. But the speed of light imposes a hard ceiling that no amount of engineering can overcome. And the distance to Proxima Centauri, at 4.24 light-years, while enormous by any human standard, is trivially small compared to almost every other destination in the galaxy, let alone the universe. The center of the Milky Way is 26,000 light-years away. The Andromeda Galaxy, the nearest large spiral, is 2.537 million light-years away. The edge of the observable universe is roughly 46.5 billion light-years distant. So what are the most serious proposals for actually doing better? The most technically plausible near-term concept is Breakthrough Starshot, announced in April 2016 by physicist and entrepreneur Yuri Milner alongside Stephen Hawking and a team of scientists. The concept involves building gram-scale spacecraft, essentially tiny sails carrying simple electronics, and accelerating them to approximately 20% of the speed of light, using an enormous ground-based laser array. At 20% of the speed of light, a probe would reach Proxima Centauri in approximately 20 years. This would be, if it worked, the fastest any human-made object has ever traveled by an enormous margin. It would still take 20 years to get there. Another 4+ years for any signal to return. No human would go, no sample would come back. The probe would weigh a few grams and survive the transit intact only if the engineering challenges, which are considerable, can be solved. Stepping up in ambition, nuclear pulse propulsion was studied seriously in the late 1950s and early 1960s under Project Orion, a classified U.S. government program that included physicist Freeman Dyson among its contributors. The core concept involved propelling a large spacecraft by detonating a series of nuclear bombs behind it, with a massive shock-absorbing pusher plate absorbing the blast and converting it into thrust. Theoretical calculations suggested speeds of 3% to 10% of the speed of light might be achievable for large spacecraft. At 10% of the speed of light, a journey to Proxima Centauri would take about 42 years. A round trip, plus communication delays, would take roughly a century. Project Orion was cancelled in 1963, in part due to the Partial Nuclear Test Ban Treaty, and the concept has never been built. Generation ships occupy a different category entirely. Rather than solving the travel time problem, they accept it. A generation ship would be a massive, self-sustaining spacecraft, carrying enough people to maintain a viable population across a journey of centuries or millennia. The people who launched would not arrive. Their great-great-grandchildren might. The ethical questions alone are enormous. What obligation do the founding generation have to the generations born mid-voyage who never chose to be on the ship? What happens if the mission changes or the destination turns out to be uninhabitable? NASA's Innovative Advanced Concepts program has funded some research into related questions, but no generation ship has been built, and the engineering of a fully self-sustaining closed ecological system for multi-generational voyages remains unsolved. Then there are the more exotic proposals, the ones that live in the space between rigorous theoretical physics and science fiction. Miguel Alcubierre, a Mexican physicist, published a paper in 1,994 inches, the journal Classical and Quantum Gravity, describing a theoretical mechanism for faster-than-light travel that doesn't technically violate Einstein's prohibition. The Alcubierre drive works by warping space-time itself, contracting space in front of the spacecraft and expanding it behind, so that the spacecraft sits inside a bubble that moves faster than light, while the spacecraft itself is stationary within that bubble. Nothing inside the bubble exceeds the local speed of light. Relativity is nominally satisfied. The problem, beyond the obvious fact that no such drive has ever been built, is the energy requirement. Alcubierre's original calculation put the energy needed at roughly equivalent to the mass energy of an object the size of Jupiter. Later, theoretical refinements have suggested the number might be reduced, but the requirement for exotic matter with negative energy density matter that has never been conclusively observed remains a fundamental obstacle. The drive is a mathematical curiosity with no known path to physical reality. Wormholes, formerly Einstein-Rosen bridges, first described mathematically by Einstein and Nathan Rosen in a 1935 paper, are theoretical tunnels through space-time that could, in principle, connect two distant regions in a kind of shortcut. They emerge naturally from the equations of general relativity. The problem is that every known class of traversable wormhole solution requires exotic matter with negative energy density to stay open. Without it, any wormhole large enough for matter to pass through would collapse almost instantly. No exotic matter with the required properties has been directly observed in nature. Quantum field theory does allow for small, negative energy effects in specific circumstances. A phenomenon called the Casimir effect provides a tiny example, but scaling this to wormhole stabilizing levels is not understood and may not be possible. The honest assessment, setting optimism aside for a moment, is this: we have no verified technology or physical principle that gets around the time barrier at interstellar distances. The fastest thing we have ever built would take 73,000 years to reach the nearest star. The most promising near-term concept, breakthrough starshot, might cut that to 20 years, but for a gram-scale probe, not a human being. Every proposal for faster travel either requires energy on scales or no civilization near our current level could produce, or requires physics that has never been observed to work. And this is for the nearest star. The Andromeda Galaxy is 2.537 million light-years away. The scale of the problem grows by orders of magnitude, with almost every destination worth naming. Distance has a way of losing meaning when the numbers grow large enough. 4 light-years sounds manageable in the same way that $1 trillion sounds manageable. The words are familiar, but the reality has ceased to correspond to any human intuition. So let's try to make this concrete. The average global human life expectancy is approximately 72 to 73 years, according to World Health Organization data from 2023. Set aside childhood, education, and the years when a person might not plausibly be a functional crew member on a spacecraft, and you have maybe 50 productive years to work with. Assume perfect health, perfect physical condition, no aging, just 50 years of available time. In that 50 years, traveling at the speed of light, you could cover exactly 50 light years. In a galaxy 100,000 light years across, a single human lifetime at the ultimate physical speed limit reaches 0.05% of the diameter of just our galaxy, not the universe. Not the local group of galaxies, just the Milky Way. Now let's put actual distances in terms that don't require abstract mathematical leaps. If the Sun were a tennis ball sitting on the ground in London, the nearest star, Proxima Centauri, would be another tennis ball sitting approximately 6,700 kilometers away, somewhere in the vicinity of Mumbai. The 2 tennis balls represent 2 stars in the same galaxy. The entire galaxy at this scale would span a circle roughly 90 million kilometers in diameter, more than half the distance from the Earth to the Sunday. And the nearest large galaxy to our own, Andromeda, would sit roughly 2 billion kilometers away at that scale, nearly the distance from the real Sun to Uranus. These comparisons don't capture the emptiness, though. Between the London tennis ball and the Mumbai tennis ball, there is essentially nothing. No other star, no other planet. Just 6,700 kilometers of void at that scale, containing virtually nothing at all. The universe is not a crowded place with points of light dotting every corner. It is almost entirely empty, with tiny islands of matter separated by distances that dwarf anything in human experience. There are an estimated 200 to 400 billion stars in the Milky Way. The total mass of the galaxy, including dark matter, is roughly equivalent to 1.5 trillion solar masses. If you were to somehow count 1 star per second, getting through all 400 billion stars in the Milky Way would take approximately 12,683 years. The observable universe contains an estimated 2 trillion galaxies, a figure revised upward in 2016 by a team led by Christopher Consolis at the University of Nottingham. Counting 1 galaxy per second, you would finish after roughly 63,400 years, longer than the estimated time for Voyager 1 to reach the nearest star. What does the universe look like at these scales of time? The light reaching your eyes from the Andromeda Galaxy tonight left its source approximately 2.537 million years ago. At that point, modern humans, Homo sapiens, didn't exist yet. The species that would eventually build telescopes to look at Andromeda was perhaps 1 million years away from appearing. The light in your eye from Andromeda tonight is ancient beyond any human frame of reference, carrying information about a galaxy as it existed before our species was born. And it took 2.537 million years just to cross the gap between neighbors. The Virgo cluster, a large cluster of galaxies of which our local group is considered a gravitational outlier, is approximately 53 million light-years away. Light leaving the Virgo cluster tonight will arrive at Earth in 53 million years. At that point, the continents will have shifted substantially. The Atlantic Ocean will be larger. Various species alive today will be extinct, replaced by descendants we couldn't recognize. The sun will still be burning, just a few % brighter, and the light from Virgo that left tonight will only then be arriving. There are regions of the universe from which light will never reach us at all, not because the light hasn't left yet, but because the expansion of space between us and those regions has been carrying those regions away from us faster than light can cross the gap. These regions are beyond what physicists call the cosmic event horizon, estimated to sit approximately 16 billion light-years from Earth. Everything beyond that horizon is, in the most literal sense, permanently beyond our reach, not just practically, but in principle. No signal, no probe, no traveler could ever cross that gulf, because space itself is expanding faster than the speed of light across that distance. The universe is not just large. Parts of it are, by the known laws of physics, permanently inaccessible to us and to everything in our causal future. The age of the universe is approximately 13.8 billion years, a figure derived from detailed measurements of the cosmic microwave background radiation, the afterglow of the Big Bang itself, first detected in 1965 and studied with increasing precision by satellites, including NASA's WMAP and ESA's Planck. The Planck 2018 data gives the age as 13.787 billion years, with an uncertainty of plus or minus about 20 million years. That light we're measuring left its source when the universe was only about 380,000 years old, when space had cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time. The CMB is a snapshot of the earliest moment the universe became transparent to light. 13.8 billion years is difficult to sit with. The Sun and Earth formed approximately 4.5 billion years ago, so the universe was already more than 9 billion years old when our solar system came into existence. Complex multicellular life on Earth has existed for roughly 600 million years. Recorded human civilization spans about 5,000 years. The universe has been running for 2.76 million times longer than the entirety of human recorded history. And even at this age, even after nearly 14 billion years of light spreading in all directions, there are portions of the universe we cannot see because they are still beyond our light cone, the volume of space from which light has had time to reach us since the Big Bang. The Sun will continue burning on the main sequence for approximately 5 billion more years before it expands into a red giant and consumes the inner planets. 5 billion years from now, if humanity or its descendants are still around, the night sky will look somewhat different. Some stars will have died. Others will have been born, but the universe will still be fundamentally recognizable. It will still be mostly empty. The nearest star will still be about 4 light years away. The Andromeda Galaxy will actually be closer in the process of merging with the Milky Way in a slow-motion collision that astronomers predict will begin in earnest in roughly 4 to 5 billion years. That collision will be less catastrophic than it sounds. The stars in both galaxies are so sparsely distributed that actual stellar collisions will be rare, but it will reshape the structure of our local region of space substantially. The deeper you push into the future, the stranger it gets. In approximately 10 to the power of 14 years, that's 100 trillion years, the last stars will have burned out, exhausting the available hydrogen. After that, the universe enters what cosmologists call the degenerate era, a cold, dark expanse populated mainly by brown dwarfs, white dwarfs, neutron stars, and black holes. Protons themselves may eventually decay, though this has never been observed and the timeline is uncertain. Black holes will evaporate via Hawking radiation over timescales that beggar comprehension. A stellar mass black hole takes roughly 10 to the power of 67 years to evaporate, while a supermassive black hole might take 10 to the power of 98 years or longer. What exists after that is the closest physics comes to true heat death, a universe at maximum entropy, where no further thermodynamic work is possible and no structure can form. Time, at that point, doesn't end. It simply continues, carrying nothing but cold equilibrium. Here is where the time barrier gets actively hostile, rather than merely passive. Not only is the universe vast and the speed limit fixed, but the universe is expanding and the expansion is accelerating. Every year, the barrier gets larger. Every moment you don't move, the most distant destinations slip further away. Edwin Hubble demonstrated in 1929 that galaxies were receding from us, and that the farther a galaxy was, the faster it appeared to be receding. This was the first observational confirmation of an expanding universe. Hubble derived this from measuring the redshift of light from distant galaxies, the way the wavelength of light stretches as its source moves away, similar to how the pitch of a passing siren drops as it recedes. The relationship he found, now called Hubble's law, stated that the recession speed of a galaxy is proportional to its distance. Double the distance, double the recession speed. This has a deeply counterintuitive implication. At large enough distances, galaxies recede faster than light. Not because those galaxies are actually moving through space at superluminal speeds. Nothing moves through space faster than light, but because the space between us and them is expanding. And at great enough distances, there's enough expanding space that the cumulative expansion exceeds the speed of light. This doesn't violate relativity because it isn't motion through space, it's the expansion of space itself. The distinction is technically important, but the practical consequence is the same. Beyond the cosmic event horizon, approximately 16 billion light-years from Earth, galaxies are moving away faster than any signal we could ever send could catch up. Those galaxies are, for any practical or physical purpose, gone. In 1998, two independent teams of astronomers studying distant Type Ia supernovae made a discovery that earned three of them: Saul, Perlmutter, Brian Schmidt, and Adam Rice the Nobel Prize in Physics in 2011. The universe was not just expanding, the expansion was speeding up. Something was pushing galaxies apart at an accelerating rate. That something was given the name dark energy, and it remains one of the greatest mysteries in physics. Its nature is unknown. Its origin is unknown. All that is clear is that it constitutes approximately 68% of the total energy content of the universe, and it is winning. The consequence for the distant future is stark. As the expansion of the universe accelerates, more and more galaxies will eventually cross beyond the cosmic event horizon and disappear from our observable universe. A few billion years from now, the Milky Way and its immediate gravitational companions, the local group, including Andromeda, will remain bound together by gravity, a small island in an otherwise increasingly empty expanse. The tens of thousands of other galaxy clusters visible today will, over tens of billions of years, recede until the light they emit can no longer cross the expanding gap to reach us. Future astronomers, if any exist, might look out at a universe that appears to contain only our own galaxy, with no evidence of the broader structure we can see today, because all the evidence will have receded beyond reach. Carl Sagan described it this way in Pale Blue Dot, his 1994 book, expanding on the famous photograph. Our planet is a lonely speck in the great enveloping cosmic dark. He was writing about Earth's position in just the solar system. Scaled to the universe, the loneliness compounds in ways that feel almost like a physical pressure. There is also an ongoing debate among physicists about the precise value of the Hubble constant, the number that describes how fast the universe is expanding per unit of distance. Early universe measurements, based on the cosmic microwave background, giving roughly 67 kilometers per second per megaparsec, disagree with local universe measurements based on standard candles like Cepheid variables and Type Ia supernovae, giving roughly 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, is about 9% small enough that it might be measurement error, large enough that some physicists suspect it points to physics not yet in the standard model. The resolution of the Hubble tension, if it turns out to require new physics, could change our understanding of the universe's expansion history and future. What does this mean for the time barrier? It means the barrier has a ratchet. It only goes in one direction. Every second that passes, the accessible universe shrinks slightly, as more of it recedes beyond the event horizon. Any civilization hoping to spread across galaxies has to work against a universe that is actively contracting its reach, not just sitting passively at a fixed distance. The problem gets harder over time, not easier, and the acceleration of that contraction is itself accelerating, driven by a force dark energy whose nature remains unknown. Here is the strange turn in this story, the place where the physics that creates the barrier might also provide a very limited, very strange escape. Time dilation, as we discussed in the first section, slows time for fast-moving travelers relative to stationary observers. At close enough to the speed of light, a traveler's subjective experience of time could compress a journey across thousands of light years into a human lifetime. So why isn't this the solution? Start with the energy required. To accelerate a spacecraft with even minimal mass to a significant fraction of the speed of light requires energy that dwarfs anything in human technological experience. The kinetic energy of a 1 metric ton spacecraft at 99% of the speed of light is roughly equivalent to the energy released by approximately 21 billion Hiroshima atomic bombs. At 99.9% of the speed of light, the energy required increases further by a factor of about 3. As you push asymptotically toward the speed of light, the energy requirement approaches infinity. No technology on any foreseeable horizon can produce energy at this scale for a crewed spacecraft. Then there's the problem of deceleration. Accelerating a spacecraft to near light speed and then doing nothing is not useful. You'd pass through your destination at near light speed without stopping. Decelerating requires the same energy expenditure as accelerating. So you need to carry enough fuel for both, which means you need to carry enormous quantities of reaction mass, which means your spacecraft is heavier, which means you need even more energy to accelerate it. And the problem compounds recursively. There's also the collision problem. At near light speeds, interstellar space, which seems empty but contains a thin scattering of hydrogen atoms and dust, becomes deadly. A single hydrogen atom encountered at 99.9% of the speed of light carries the energy of a high-speed rifle bullet. At the density of interstellar space, a spacecraft would encounter enough of these impacts to be destroyed long before reaching its destination. Shielding solutions have been proposed, ablative shields, magnetic fields, but none has been demonstrated to work at the required scales. The time dilation solution also produces what is called the twin paradox, one of the most famous thought experiments in physics. If you leave Earth on a fast spacecraft while your twin stays behind, your twin will age much more quickly than you. When you return, your twin will be old or dead while you may have aged only a few years. This is not a paradox in any mathematical sense. It is a straightforward consequence of special relativity, and it has been confirmed experimentally. But it means that any civilization that sends travelers to distant stars via near light speed travel effectively severs them from their origin culture. The travelers arrive at their destination to find that centuries or millennia have passed at home. Whatever they left behind is gone. Whatever mission they were sent on may no longer have relevance. They are not explorers returning with data. They are, in a real sense, time travelers who have been catapulted into the future with no way back. This cuts to the heart of one of the deeper philosophical problems that time creates for interstellar civilization. Even if time dilation makes the traveler's subjective journey manageable, the universe keeps running at its own pace while you travel. The destination is 100 light years away. You travel at near light speed and arrive in what feels like a few years to you, but 100 years have passed at both origin and destination. The contact time between origin and destination, the lag in any communication, is still 100 years at minimum, regardless of how the traveler experienced the journey. Building a coherent interstellar civilization, one with shared culture, governance, economy, even language, under conditions where any message takes decades to centuries to cross the distances between nodes, may be functionally impossible. Language alone drifts significantly in just a few centuries. Institutions collapse and reform on similar timescales. What holds an interstellar network together when a request for help takes 200 years to arrive and a response takes another 200 years to return? Carl Sagan, whose 1980 television series Cosmos introduced these questions to a popular audience in ways that have endured, framed the scope of the challenge with characteristic directness. The cosmos is all that is, or ever was, or ever will be. That sentence, read carefully, is not triumphalist. It is a reminder of scale, that the cosmos encompasses everything, including the barriers, including the distances, including time itself. No discussion of time as a cosmic barrier is complete without sitting with the Fermi paradox, because the paradox stated simply is that the universe appears to contain no evidence of civilizations that have solved the problem, and that silence is itself data. In 1950, during a lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi posed what seemed like a casual question. If the universe is so vast, so old, and if the conditions for life appear to exist in so many places, then where is everybody? The question has echoed through physics and astronomy ever since. The Drake equation, formulated by astronomer Frank Drake in 1961 at the National Radio Astronomy Observatory, attempted to estimate the number of communicating civilizations in the Milky Way by multiplying together the various factors thought to determine that number: the rate of star formation, the fraction of stars with planets, the fraction of planets where life arises, the fraction where intelligent life arises, the fraction that develops technology, and the length of time such civilizations remain detectable. Depending on how optimistically or pessimistically you fill in those variables, the equation produces estimates ranging from far less than one civilization in the galaxy to millions. SETI, the search for extraterrestrial intelligence, an ongoing effort with roots going back to Drake's own Project Ozma in 1960, has been scanning the sky for decades without finding a verified signal. The closest candidate remains the WOW signal, detected on the 15th of August, 1977, by astronomer Jerry Ayman using Ohio State University's Big Ear Radio Observatory. Ayman circled the unusual data on a printout and wrote "WOW" next to it, giving the signal its name. It has never been repeated or confirmed as extraterrestrial in origin. The silence matters for our subject because one of the leading categories of explanation for the Fermi paradox involves time as the fundamental obstacle. Civilizations arise, but they can't cross the distances. Signals take millennia to travel. By the time a signal from one civilization reaches another, the sending civilization may be gone. By the time any response could return, the receiving civilization may have changed beyond recognition. Interstellar communication operates on timescales that exceed the lifespan of typical civilizations. Even if the galaxy is full of life, civilizations might be so separated in both space and time that they miss each other entirely, ships passing in the night, where the night lasts millions of years. The Great Filter hypothesis, developed by economist Robin Hanson in 1998, posits a different angle on the same silence. The hypothesis suggests that somewhere in the process of evolving from simple chemistry to a civilization capable of spreading through the galaxy, there is a step so improbable or so destructive that almost no civilization makes it through. The unsettling version of this idea is that the Great Filter might lie ahead of us, not behind us, meaning that the thing which wipes out most advanced civilizations is something we haven't yet encountered. Some candidates are technological, engineered pandemics, nuclear war, artificial intelligence systems that optimize for goals incompatible with biological life. Others are temporal and physical. Perhaps the time required to cross interstellar distances is simply so enormous that every civilization exhausts its resources, fragments under internal pressures, or undergoes enough change to lose the shared purpose needed to sustain a multi-century or multi-millennium project. What the Fermi paradox ultimately illustrates is that the time barrier isn't just a physics problem, it is a civilizational problem. Even if the physics were solved, even if some propulsion system brought the nearest stars within a 50-year journey, maintaining the institutional coherence, cultural continuity, and political will to sustain interstellar programs across the necessary timescales would be a challenge unlike anything in human history. The Voyager 1 mission, launched in 1977 and still operational as of this writing, represents one of the longest-running examples of sustained human institutional effort in space, and it remains less than 1/70 zeroth of the way to the nearest star. Stephen Hawking addressed this challenge directly when he co-announced Breakthrough Starshot in April 2016. His framing was characteristically stark. "I don't think the human race will survive the next 1,000 years unless we spread into space." He wasn't optimistic about the timeline. He was arguing that the alternative, remaining confined to a single fragile planet, was the more dangerous bet. Whether that urgency translates into the sustained, multi-generational, institutional effort that actual interstellar travel would require is a separate question, and one that no amount of enthusiasm at press conferences has yet answered. All of this has been cosmic in scale, and deliberately so, but it's worth pulling back to the human experience of time, because the barrier is not only measured in light years and spacecraft velocities. It is measured in human lifespans, in the brevity of individual lives against the vastness of cosmic time. And that juxtaposition is where the emotional weight of this subject sits. A human lifetime of 72 or 73 years, the current global average is, from a cosmic perspective, essentially instantaneous. The universe has been running for approximately 13.8 billion years. A human lifetime represents approximately 0.00000005% of the age of the universe. If the universe's history were compressed into a single calendar year, with the Big Bang at midnight on January 1st, then the entirety of recorded human history from Sumerian writing to the present day would occupy the final 0.3 seconds before midnight on December 31st. Voyager 1, launched in 1977, has been traveling for less than a human lifetime, and it is still 73,000 years short of the nearest star. This brevity is not merely philosophical, it has direct practical consequences for any interstellar program. The scientists who designed and built Voyager 1 are mostly dead or very old. The institutional knowledge, accumulated over decades of the mission's operation, has had to be rebuilt and maintained by successive generations of engineers and scientists. NASA's ability to communicate with Voyager 1 depends on the Deep Space Network, a system of antenna arrays maintained continuously since 1963. The mission has been sustained by an unusual combination of institutional durability, political continuity, and the dedication of individual people who were not alive when the spacecraft launched. Now scale that challenge by a factor of 1,000 or 1,000,000. An interstellar mission would require not just decades of institutional commitment, but centuries. No political institution in human history has sustained uninterrupted programmatic focus for centuries. The Roman Empire lasted about 5 centuries before fragmentation. The Catholic Church, one of the longest-lived institutions in Western history, has lasted about 2 millennia, but with enormous internal transformations along the way. No space agency, no government, no corporation has a multi-century track record of sustained technical program management, and yet that is precisely what interstellar travel demands. The physicist Michio Kaku, who has written extensively about the future of civilization and the cosmos, has framed this in terms of what he calls a Type 1, Type 2, and Type 3 civilization on the Kardashev scale, a classification proposed by Soviet astronomer Nikolai Kardashev in 1964. A Type I civilization harnesses all the energy available on its home planet. A Type 2 harnesses the energy of its star. A Type 3 harnesses the energy of its entire galaxy. By Kaku's estimates, humanity is currently at roughly Type 0.7. We have not yet achieved the full utilization of Earth's available energy. Getting to Type I might take another century or two at current rates of growth. Getting to Type 2, a prerequisite for serious interstellar capability, according to most analyses, would take millennia. The gap between where we are and where we would need to be to cross even the nearest interstellar distances within a human lifetime is not incremental, it is categorical. Time is also the enemy of any given scientific or engineering effort because of the way it compounds uncertainty. The further out you project, the more variables accumulate and the less confident any prediction becomes. This isn't defeatism, it's basic epistemology. Planned missions with horizons of a decade are uncertain. Planned missions with horizons of a century are extremely uncertain. Planned missions with horizons of a millennium might as well be mythology for all the reliable planning guidance they can offer. The people who would actually conduct an interstellar mission haven't been born yet. Their culture, their motivations, their political context, their relationship to the mission's original goal are all unknowable from here. And yet, sitting with the full weight of all this, there is something worth noting about human beings specifically. We are, among all the species we know of, the only ones who appear to grapple seriously with their own cosmic insignificance and continue building anyway. The ancient Egyptians built the pyramids under the shadow of mortality and the certainty that whatever gods they served might outlast any stone. Medieval cathedral builders began projects they knew would not be completed in their lifetimes, designing structures for generations of future worshippers they would never meet. The scientists behind the Voyager program chose a trajectory that would carry their spacecraft out of the solar system, knowing that no one then alive would see it reach another star. There is something distinctly human about building toward timescales that exceed human lives, and that instinct, more than any specific technology, may be the most relevant variable in the very long game of whether this species ever crosses the cosmic distances. We've spent most of this video dealing with time as a practical barrier and a relative quantity. But there's a deeper layer of strangeness worth examining, because the more carefully physicists look at what time actually is at the fundamental level, the more genuinely uncertain the picture becomes. The second law of thermodynamics states that entropy roughly, the degree of disorder in a closed system, tends to increase over time. This is why ice melts but doesn't spontaneously freeze, why coffee cools rather than heats up in a cold room, why aging happens in one direction. The arrow of time, as the physicist Arthur Eddington named it in 1927, flows in the direction of increasing entropy. The interesting thing is that almost all the fundamental laws of physics are time-symmetric. They work equally well whether time runs forward or backward. The equations of quantum mechanics, of classical mechanics, of electromagnetism, run them in reverse, and they remain valid. The arrow of time, the reason we experience a past and a future rather than a symmetric smear of moments, appears to arise not from any fundamental law, but from the specific initial conditions of the universe, which happen to start in a state of very low entropy at the Big Bang. In that sense, the entire arrow of time, the fact that time flows in any direction at all, is a consequence of the Big Bang rather than a fundamental feature of reality. Roger Penrose, one of the most creative mathematical physicists alive, has proposed a cosmological framework called conformal cyclic cosmology, in which the universe undergoes successive aeons, each beginning with a Big Bang-like event and ending in a heat death, which then transitions into the Big Bang of the next eon. In this model, time doesn't truly end. It transforms, in a way that Penrose argues is mathematically consistent. The model is speculative and contested, but it represents a serious attempt to grapple with what happens to time at the ultimate scales of the universe's history. Lee Smolin's work pushes in a different direction. In Time Reborn, published in 2013, Smolin argues that the block universe view, in which past, present, and future all exist with equal reality and time is fundamentally an illusion, leads to scientific and philosophical dead ends. His argument is that the laws of physics themselves evolve over time, that the universe has a genuine history that cannot be captured in any timeless mathematical structure, and that time is more real, not less real, than the space-time diagrams of relativity suggest. Smolin's view is a minority position among physicists, but it has serious adherents, and the debate it represents between time as illusion and time as the most fundamental thing remains unresolved. At the quantum scale, time behaves in ways that are even less intuitive. Quantum mechanics predicts that particles can, in a sense, borrow energy from the future. For brief periods, this is the basis of quantum tunneling. The process by which particles pass through barriers they classically shouldn't be able to cross, and which underlies everything from radioactive decay to the operation of transistors in every computer on Earth. Quantum entanglement, the correlations between particles regardless of the distance between them, was famously called spooky action at a distance by Einstein, who found it disturbing. The correlations appear instantaneous, but no information travels between entangled particles, so the speed of light constraint is not violated. What time means for an entangled quantum system is a question that doesn't have a clean answer. At the very smallest scales, at the Planck scale, below 5.39 times 10 to the power of negative 44 seconds, the standard framework of spacetime itself breaks down. General relativity and quantum mechanics are incompatible mathematical frameworks, and their incompatibility becomes acute at the Planck scale. String theory, loop quantum gravity, and other attempts at a theory of quantum gravity all make different predictions about what time looks like at this scale, whether it is continuous or discrete, whether it exists at all as a fundamental quantity or emerges from something more primitive. No experiment has yet been able to probe the Planck scale directly. The physics there is genuinely unknown. The concept of the specious present, the psychological window of time that feels like now, is itself a curious thing. Neuroscience suggests that human consciousness integrates sensory information over an interval of roughly 2 to 3 seconds to produce the experience of the present moment. The now that feels immediate and direct is actually a constructed average of slightly past events. We are always, in a small but real sense, living slightly in the past. The brain builds a model of the present from information that has already happened and retroactively stitches it together into the feeling of immediacy. At one end of the scale, the Planck time, 10 to the power of negative 44 seconds time, may not exist in any recognizable form. At another end, the heat death, some 76 years in the future, time continues but contains nothing. In between, for a brief window of about 10 to the power of 14 years, during which stars burn, life is conceivable. That window is now. We are in it. And within that window, a species that has been technically sophisticated for perhaps 200 years is grappling with distances and timescales that the universe seems to have designed specifically to be unreachable. Against this backdrop of grand theory and impossible scale, it's worth pausing to appreciate what has actually been accomplished, the small, genuinely extraordinary things human beings have managed to do, and what they tell us about both the magnitude of the problem and the peculiar stubbornness that drives people to keep working on it anyway. Voyager 1 launched on the 5th of September, 1977, propelled by a Saturn-derived Titan IIIe Centaur rocket into a trajectory designed to take advantage of a rare planetary alignment, a geometric arrangement that occurs roughly once every 175 years, that allowed the spacecraft to use gravitational assists from Jupiter and Saturn to reach escape velocity from the solar system. The spacecraft carries a golden record, a gold-plated copper disc containing sounds and images selected to represent life and culture on Earth, curated by a committee that included Carl Sagan. Greetings in 55 languages, music from Bach and Chuck Berry, and a Navajo night chant, the sound of a mother's first words to her newborn child. It was, as Sagan described it, a message in a bottle cast into the cosmic ocean. NASA confirmed in 2012, based on data showing changes in the charged particle environment around the spacecraft, that Voyager 1 had entered interstellar space, the first human-made object to do so. The formal announcement came in August 2013, and it was a genuine milestone in human history. As of this writing, Voyager 1 is approximately 23.5 billion kilometers from Earth, and its radio signals, traveling at the speed of light, take more than 22 hours to reach the deep space network antennas on Earth. The spacecraft's power comes from radioisotope thermoelectric generators, RTGs, that are gradually losing output. NASA engineers project that scientific instruments will need to be shut down one by one over the coming years as power becomes insufficient. Voyager 1 will eventually fall silent, becoming a permanent artifact of the early space age drifting silently through interstellar space. At approximately 38,000 miles per hour, Voyager 1's distance from the Sun grows by about 3.6 astronomical units per year, an astronomical unit being the average Earth-Sun distance of about 93 million miles. The distance to Proxima Centauri is about 268,770 astronomical units. At this rate, Voyager 1 would reach the vicinity of Proxima Centauri in approximately 73,000 years, though it is not headed in that direction. It will pass closer to a different stellar neighbor, AC plus 793888, in approximately 40,000 years. The pale blue dot photograph, taken by Voyager 1 on the 14th of February 1990 at the request of Carl Sagan, was captured when the spacecraft was approximately 3.7 billion miles from Earth. Earth appears in the photograph as a tiny, barely visible point of pale blue light, a fraction of a pixel against the backdrop of space. Sagan's accompanying text, later included in his 1994 book, remains one of the most quietly devastating pieces of scientific writing in the 20th century. Look again at that dot. That's here, that's home, that's us. He wasn't being nihilistic, he was being precise. The Parker Solar Probe, launched in August 2018, represents the current frontier of human speed achievement. During perihelion passes its closest approaches to the Sun, the spacecraft reaches approximately 430,000 miles per hour, nearly 12 times faster than Voyager 1. The probe uses repeated gravitational assists from Venus to lower its perihelion, bringing it ever closer to the solar surface. Its heat shield must withstand temperatures approaching 1,400 degrees Celsius. At its peak speed, it remains more than 1,500 times slower than the speed of light. Even if somehow maintained at this velocity indefinitely, which it cannot be, the probe is on a solar-focused orbit, not an interstellar trajectory. The journey to Proxima Centauri would take about 6,633 years. The James Webb Space Telescope, launched on the 25th of December 2021, sits approximately 1.5 million kilometers from Earth at Lagrange Point 2 and has been providing observations since mid-2022. Its infrared capabilities allow it to observe light from galaxies that existed as little as 200 to 300 million years after the Big Bang light that has been traveling for over 13 billion years. The JWST doesn't transport us anywhere, but it extends the reach of human perception across distances and timescales that no spacecraft will reach in the foreseeable future. Looking at light from 13 billion years ago is not travel, but it is something. It is evidence that the universe was there and that it was doing things long before any species existed to observe it. There is a strange thing that happens when you sit with all of this long enough. The scale stops being paralyzing and starts being clarifying. The universe is not indifferent to us in the way that a hostile force is indifferent. It simply operates on timescales and distances that bear no relationship to the scale on which human lives or human institutions operate. The barrier isn't personal, it isn't directed at us, it's just physics. Einstein, in the letter to the Besso family written in 1955, consoled Michel Besso's grieving relatives by pointing to the block universe. The distinction between past, present, and future is only a stubbornly persistent illusion. Whether or not you accept the block universe interpretation of relativity, and there are serious physicists who do not, the sentiment underlying that letter has a kind of austere comfort to it. If past and future exist with the same reality as the present, then what feels like loss is, in some sense, just a different kind of distance. The person is not gone. They have become unreachable in time rather than in space. The physics of relativity doesn't make that grief smaller, but it does suggest that the universe treats spatial and temporal distance as aspects of the same thing, and human beings have always found ways to reach across distance. Stephen Hawking, whose work on black holes and theoretical cosmology pushed physics forward across several decades, wrote in A Brief History of Time in 1988, "Even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe? That question, not the equations, but the fire in them, is the one that time ultimately leads to. The equations of general relativity describe a universe in which nothing with mass can exceed the speed of light, in which space is expanding and accelerating, in which the distances between stars are incomprehensible and growing. All of that is in the equations. What breathes fire into them, what makes it the specific universe we happen to occupy, with its specific speed limit and its specific expansion rate and its specific age, is not in the equations at all. From the pale blue dot perspective, Earth is one world among potentially billions of worlds. in one galaxy among 2 trillion galaxies, in a universe 93 billion light-years across that has been running for 13.8 billion years and will continue for durations that make all of recorded human history look like a rounding error. The time barrier is enormous, and it may be permanent. There is no guarantee that humanity will solve it. There is no physical law that promises a species the ability to cross the distances its instruments can see. The universe is under no obligation to be navigable, but there is this. Humans are the only thing we know of in the universe that is even asking the question. Voyager 1, drifting at 38,000 miles per hour through interstellar space with its golden record of music and voices, is a product of minds that looked at the distances and chose to build something anyway. Breakthrough Starshot, with its proposal to send gram-scale laser sails to the nearest star, is a product of minds that looked at the physics and found a way to push within it rather than against it. The James Webb Space Telescope is a product of minds that, unable to travel to the early universe, built an instrument to look back at it across 13 billion light-years of space and time. None of that solves the time barrier, but it demonstrates something about the peculiar nature of the species facing it. We are not equipped by biology to cross interstellar distances. Our lifespans are wrong. Our bodies are wrong. Our speeds are wrong by many orders of magnitude. And yet something in the architecture of the human mind finds the distances not only comprehensible but personally significant, worth studying, worth building toward, worth the astonishing investment of time and resources that has gone into even our most preliminary steps outward. Carl Sagan, who understood this better than almost anyone, put it directly in Cosmos in 1980. The cosmos is all that is, or ever was, or ever will be. That sentence includes us. We are not outside looking in at the cosmos. We are a piece of the cosmos that has become capable of looking at itself. The same physical matter that makes up the most distant galaxies makes up the neurons firing as you process this sentence. The same laws of physics that impose the time barrier are the laws that produce the conditions for life to arise on this planet in the first place. The barrier and the observer are made of the same stuff, governed by the same rules, and embedded in the same four-dimensional fabric of space-time. At this point, it's worth doing a final, honest accounting of the proposed solutions to the time barrier, now that the full scope of the problem is clear. Near light speed, travel with time dilation. In theory, this works. The physics is correct. Time dilation at near light speed would compress a traveler's subjective journey dramatically. The obstacle is energy. The energy required to accelerate a crude spacecraft to relativistic speeds using any known physics is far beyond the reach of any conceivable near-term technology. Antimatter propulsion, annihilating matter and antimatter to extract maximum energy, is the most theoretically efficient approach we know of. And even that faces the problem that producing and storing antimatter in the quantities needed is extraordinarily difficult. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, produces quantities of antimatter that could power a light bulb for a fraction of a second. Scaling that to a spacecraft propulsion system is not an engineering problem with a near-term solution. It is multiple orders of magnitude beyond current capability. Breakthrough Starshot, the most technically accessible near-term concept. Laser-propelled gram-scale sails at 20% of the speed of light are at least theoretically achievable, with technologies whose basic components exist: powerful lasers, thin film reflective materials, microelectronics. The challenges are substantial atmospheric distortion of the laser beam, the precision required to maintain focus across the acceleration distance, the durability of the sail during acceleration, the question of how the probe communicates from the destination, but they are engineering challenges rather than physics impossibilities. This concept represents humanity's most realistic path to reaching another star system within a century, and it would carry no human beings. Nuclear pulse propulsion, technically sound, in principle, the physics works. Project Orion demonstrated on paper that speeds of several % of the speed of light are achievable. The obstacles are political. Nuclear detonations in space are banned by treaty and practical. The engineering of a spacecraft that repeatedly absorbs nuclear blasts while maintaining structural integrity is challenging, though the Orion team believed it was solvable. This is probably the most credible approach to crewed interstellar travel that doesn't require entirely new physics, and it has been largely abandoned due to political and regulatory constraints rather than technical impossibility. Generation ships. Avoid the speed problem by accepting the time. No new physics required. The engineering challenges of building a fully self-sustaining biosphere aboard a spacecraft for multi-generational voyages are immense but don't violate any known physical principles. The ethical and social questions are arguably harder. What governance structure maintains purpose and mission integrity across generations? What happens to people born and raised aboard the ship who never chose the mission? How is genetic diversity maintained? These questions have no tested answers because nothing like a generation ship has ever been built. Alcubierre warp drive, mathematically consistent within general relativity, requires exotic matter with negative energy density that has never been observed in the required quantities or configurations. Original energy requirements were equivalent to the mass energy of Jupiter. Later theoretical work has suggested refinements, but no version has been reduced to anything near engineering feasibility. Faces additional problems related to causality and the ability to actually control or stop the warp bubble, currently in the category of interesting theoretical constructs with no known path to physical realization. Wormholes, consistent with general relativity, first described by Einstein and Rosen in 1935. All traversable wormhole solutions require exotic matter with negative energy density to prevent collapse. The Casimir effect demonstrates that small negative energy densities are physically possible in quantum mechanics. But the gap between the Casimir effect and a macroscopic traversable wormhole is enormous, and no bridge between the two is known. Currently in the same category as the warp drive, mathematically interesting, physically undemonstrated. Cryogenic suspension would solve the human lifespan problem if it could be made to work. No fundamental physical obstacle to pausing biological processes at very low temperature. The question is whether complex biological systems, particularly the brain, can be preserved through cooling and rewarming without damage at the cellular and molecular level. Current cryonics research has not demonstrated successful revival of large mammals from whole-body vitrification. The technical barriers are significant and have not been overcome as of 2024. The honest summary is no known technology, verified physics, or demonstrated biological technique currently provides a path to crossing interstellar distances with living human beings within a human lifespan or any politically sustainable timeframe. The nearest star is 4.24 light-years away. The fastest thing we have built would take 73,000 years to reach it. The most promising concept for doing better laser sails, accelerated to 20% of the speed of light, might reach it in 20 years with a spacecraft that weighs a few grams. Every other proposed solution is either at the frontier of theoretical physics or requires physics that has never been demonstrated to exist. Given all of this, the immovable physics, the incomprehensible distances, the missing technologies, why does any of it matter now? Why study a problem that the best current thinking suggests won't be solved for centuries at minimum and may never be fully solved? Several reasons. First, because understanding the barrier is the prerequisite for working on it. You cannot engineer around a problem you don't understand. The history of physics is full of moments where limitations that seemed permanent turned out to encode possibilities that were simply invisible until the right framework was developed. Newtonian physics said that simultaneity was absolute. Einstein showed it wasn't, and in doing so opened the door to technologies, from nuclear energy to GPS, to the semiconductor physics underlying every modern computer. The quantum mechanics that seemed like abstract philosophy in the 1920s became the foundation of every transistor, laser, and MRI scanner. The limits we understand today are always potentially hiding the principles that will be exploited tomorrow. Second, because the time barrier applies not just to interstellar travel, but to our understanding of what the universe contains. The James Webb Space Telescope's observations of the early universe are limited by the same physics. We can only see light that has had time to reach us. The cosmic microwave background represents the earliest moment from which light can have traveled to us. What existed before 380,000 years after the Big Bang, before the universe became transparent to light, is observable only indirectly, through its effects on what came after. The barrier is epistemological as well as physical. Time limits not just where we can go, but what we can know. Third, because the time barrier is the context in which questions about the long-term future of humanity have to be understood. Stephen Hawking's comment that the human race will survive the next 1,000 years only if we spread into space is meaningful precisely because of what interstellar travel actually requires. 1,000 years, the duration Hawking was working with, is perhaps long enough to get to Mars, perhaps long enough to establish a self-sustaining presence in the outer solar system. It is nowhere near long enough, at current technological trajectories, to reach another star. The solar system is the range of practical human expansion for the foreseeable future, and the solar system, while vast by human standards, is a single point in the universe, a single address, subject to the same catastrophic risks as any other single address. Fourth, and perhaps most fundamentally, because the time barrier is where physics and philosophy touch directly, in a way that affects not just how we think about space travel, but how we think about what it means to be a conscious being embedded in time. The block universe view that arises from relativity in which all of time exists simultaneously, and our sense of a flowing present is constructed rather than fundamental, has implications for how we understand memory, anticipation, free will, and identity. The arrow of time, which rises from thermodynamics rather than fundamental physics, determines the entire structure of cause and effect. The Planck time, at which space and time lose their meaning, sits as a boundary on knowledge itself. These are not merely academic puzzles. They are the underlying structure of the world we inhabit. We began this video with a simple statement: 2 trillion galaxies, the nearest large 12.537 million light-years away. The light now reaching your eyes having left before our species existed. The cosmos is all that is, or ever was, or ever will be, and the biggest thing standing between any conscious observer and most of that cosmos is time itself. Not distance exactly, because distance and time in a relativistic universe are the same thing. Not technology, because technology can improve, but cannot repeal physics. Not will, or imagination, or funding. Time itself, the basic architecture of the universe's four-dimensional structure, the thing that puts every distant galaxy behind a wall that is not made of matter but of seconds and years and eons, stacked so deep that even light, the fastest thing in the universe, barely makes a dent. Pull back all the way, start from the beginning of what we covered. Time is not a fixed river. It bends, dilates, and flows at different rates depending on how fast you're moving and how strong the gravity around you is. This has been verified experimentally, from atomic clocks on aircraft to the GPS satellites that adjust their clocks by 38 microseconds every single day to account for relativistic effects. It is not speculation. The universe runs on relativistic time, not on human intuition about clocks. The speed of light, 670 million miles per hour, is both the fastest speed at which information can travel and the unit by which cosmic distances are measured. The nearest star is 4.24 light-years away. The nearest large galaxy is 2.537 million light-years away. The observable universe is 93 billion light-years across. Our fastest spacecraft would take 73,000 years to reach the nearest star. The most promising near-term proposal for doing better breakthrough Starshot's laser sails might reach it in 20 years, carrying a probe that weighs a few grams. The universe is expanding, and the expansion is accelerating, driven by dark energy whose nature remains unknown. Regions of the universe beyond approximately 16 billion light-years are already beyond the cosmic event horizon, permanently unreachable by any signal or traveler we could ever send. Because space between here and there is expanding faster than light, the accessible universe is shrinking, not growing. The Fermi paradox, the silence of the sky, despite the apparent abundance of conditions for life, may itself be a consequence of the time barrier. Civilizations separated by hundreds or thousands of light years might be communicating across timescales that exceed their own lifespans. Any signal sent today from Earth at the speed of light would take 4.24 years to reach even the nearest star, and that star appears to be uninhabited. At the deepest level, the nature of time itself remains genuinely unresolved. The block universe interpretation of relativity says past, present, and future all exist. The second law of thermodynamics says time has a direction. The Planck scale says there's a level below which time loses meaning. Quantum mechanics says particles can tunnel through barriers. Entangled states show correlations that appear instantaneous, and the rules operate symmetrically in both temporal directions. The contradiction between general relativity and quantum mechanics, the two most successful physical theories ever developed, becomes acute at the Planck scale and has not been resolved. What time fundamentally is remains one of the deepest open questions in physics. And humanity, this 200-year-old technological civilization, this species whose entire recorded history fits into the last 0.3 seconds of the cosmic calendar year, this particular collection of matter that has become curious about the universe it finds itself in, is pressing against this barrier with the tools it has. Voyager 1, golden record and all, drifting through interstellar space at 38,000 miles per hour, the James Webb Space Telescope, looking back 13 billion years. Breakthrough Starshot, its laser arrays still on drawing boards, the researchers calculating wormhole geometries and exotic matter requirements, the engineers trying to keep an aging spacecraft talking from 22 light hours away. None of it solves the problem. Not yet, maybe not ever, at the deepest scales. But the thing that made Sagan circle the 14th of February 1990 on his calendar to make sure Voyager 1 turned its camera back toward home before leaving the solar system forever, the instinct that made him want to see what home looked like from out there, from 3.7 billion miles away. Even though it was just a pale blue dot against the dark, that same instinct is in the equations, in the designs, in the continued beaming of signals toward a machine no wider than a dinner plate that has been drifting alone through the interstellar medium for more than a decade. The time barrier is real, it is physical, it may be the most fundamental obstacle in the universe. And yet here we are, taking its measure, building tools to look past it even when we can't cross it, building the first very small, very slow, very tentative vehicles to push against it anyway. That might not seem like much against 93 billion light years, but it is something. It is the only kind of something we know how to make.